Welcome all. So, last time we started the chapter on 2 degree of freedom analysis. We looked into the different formulations. We took a real life system, we took a beam, we looked into how to change for single degree of freedom system as we have done earlier. After that, we delved into the 2 degree of freedom approximations. We talked about the degrees of freedom, the amount of independent degrees of freedom required in order to describe a system as a single degree, 2 degree or even higher degrees of freedom system. Then we took one example in which we evaluated out the frequency of the system, we evaluated out the response of the system, and after the general formulation we took a specific case of the example and we tried to solve for this. So, today we will continue from there, we will pick up from there and we will again delve into the intricacies of the 2 degree of freedom system. Okay. So, right now we have taken one example in which again we are given a 2 degree of freedom system. Okay. So, here we are looking into the free vibration undamped system. Free vibrations means the forcing function is 0, and undamped system means the damping is 0. Okay. So, the system is being defined by the inertia effect and the stiffness effect, okay, and some initial conditions will be applied so that the system is going to vibrate. Okay. So, in this particular example, the value of the stiffness is given, okay, and the value of the mass is given, okay, and one initial condition is applied which causes the disturbance in the system. Okay. The degree of the freedom is defined as the horizontal translation of mass m1 and the other degree of freedom is defined as the horizontal translation of the other mass. Okay. So, as a rule, last time as we have seen, to evaluate the number of degrees of freedom for any given system, we followed this simple rule. Okay. The number of degrees of freedom of the system equals to the number of mass in the system times the number of possible type of motion for each mass. Okay. So, we looked into different types of system. Okay. So, here number of mass is 1 and it can move in the horizontal direction and it can move in the vertical direction. So, 2 motions. So, total degree of freedom is, so this is a 2 degree of freedom system. Okay. So, building on this thing we will look into the specific example now. Okay. So, number of mass in the system, there are 2 mass in the system. So, 2 masses. Okay. So, for mass 1 it can move in the horizontal direction, there is no vertical motion. So, for first mass motion will be in one direction, plus for the second mass 1 mass and the motion will again be in the horizontal direction. So, 1 cross 1, 1 degree of freedom. Okay. So, in totality we have 2 degrees of freedom. Okay. So, we established that there are 2 degrees of freedom. Okay. The values of m1, m2 and k1, k2 and k3 are given here. Okay. There is no forcing function in the system. So, this is a case of free vibration and there is an initial condition in the system which causes the system to vibrate. There is no damping in the system. Okay. So, this becomes a case of undamped system. Okay. So, as earlier we draw the free body diagram of the system. Okay. So, what we do is that we take this system out, okay, and we take out this system separately. Okay. So, when we do that, okay, so the system 1, okay, so this is the degree of freedom x1 and we say that a pseudo acceleration is being applied. So, m1 x1 double dot is the value of the acceleration. If it is moving in the right direction, the stiffness will be applied. So, that will be k1 x1, okay, and then we write down the second mass, okay, with degree of freedom x2, okay, again a pseudo acceleration will be applied m2 x2 double dot, okay, and since this one is also moving this way, so a stiffness k3 times x2 will be applied. Now, if you look closely here, okay, there is one more spring out here. Okay. So, the net motion of this spring is x1 minus x2. Okay. So, this is the net motion of the system. Okay. So, x1 minus x2. Okay. And in the first case, this spring is going to oppose the motion towards the right. Okay. So, this is causing here, okay. And in the second case the other side it will be applied. Okay. So, this becomes K2 x1 minus x2 and again K2 x1 minus x2. Okay. So, now we have written down all the forces in the system. Okay. So, after that we will write down the equation of motion, summation of forces in the horizontal x direction as positive. Okay. So, we write down the equation of the motion for the first body, we write down the equation of the motion for the second body. Okay. And after rearranging we get these two equations of motion. If you look here, x1 and x2 are appearing in both the equations. So, this is called the coupled equation. Okay. So, from there we write down the equation in the matrix form as before, the forcing function is 0. Okay. After that there are always two parts to the solution, one is the steady state response and one is the transient response, or the particular response and the complementary response. In this particular case the forcing function is 0. So, the steady state or the particular part is 0. The transient or the complementary response we assume it to be following a sinusoidal function, okay, like we have done earlier in case of single degree of freedom system. Okay. So, x1 and x2 will follow a sinusoidal path. Okay. So, this one we assume that this is coming from the shape function. Okay. This is coming from the shape functions phi and this is from the time dependent part q. Okay. So, each degree of freedom will be a summation of from the time dependent part coefficient and the shape function. Okay. So, this was the displacement function or the degrees of freedom function, and then we write down the acceleration component of the system. Okay. So, after substituting the acceleration component into the equation, we write down the total equation in the form of the time dependent component. Okay. So, we rearrange the equation, okay, and then we substitute the value of k1, k2, k3, m1 and m2 in this particular equation. Okay. So, we get this particular equation. Okay. So, after that for a non-trivial solution, okay, the determinant of this part, okay, the determinant of this part should be 0, because if a1 and a2 becomes 0, okay, if this component is 0 then there will be no motion in the system. Okay. So, in order to have a non-trivial solution, the determinant of this part should be 0. Okay. So, the same thing we have done earlier also. Okay. When we are looking into the general solution, okay, when we are doing the general solution, okay, then again we did the same thing. We use the degrees of freedom in terms of time dependent component and the shape function. Shape functions we are assuming a sinusoidal motion, and after that we wrote down the q for, and for the non-trivial solution the determinant of this matrix should be equal to 0. Okay. So, after that we wrote down the function in terms of omega, okay, and we used this thing as a quadratic function, okay, and this is the solution for the quadratic function, and after that we evaluated the values of omega. Okay. So, omega corresponds to the natural frequency of the system. So, there will be two solutions. So, there will be two natural frequencies of the system. Okay. So, we are following the same formulation here also. Okay. So, in this particular problem what we did was we wrote down the given values of the system, okay, and the determinant of this matrix should be 0. So, determinant of this matrix should be 0. So, we wrote down in terms of omega square is substituted as x, and we wrote down the quadratic equation, okay, and from there, okay, we wrote down the equation for the quadratic solution. Okay. So, in order to calculate this thing we used, so this was the quadratic equation. Okay. So, then we wrote down the values of x minus b plus minus root over b square minus 4ac divided by twice a. The same thing we will be using here also. So, this is a, b, c. Okay. So, minus b plus minus root over b square minus 4ac divided by twice of a. Okay. So, the value of b is minus of 85 plus minus 85 square minus 4, a is 10 and C is 150 and then twice of A, 20, 2 into 10. Okay. So, we use this equation and from here we calculate the value of omega 1 and omega 2. So, the value of omega 1 comes out to be 1.5811 and omega 2 is 2.449. So, actually there are two values, okay, plus minus of this, plus minus of this. Okay. Since the frequency cannot be negative, we are ignoring the two minus terms. Okay. So, we get the first frequency, we get the second frequency. Okay. So, after that what we did was A1 and A2. Okay. So, we calculated the frequencies, now we are trying to calculate the mode shape. Okay. So, we are substituting. So, what we will do is that we will use this same equation and to get the first mode shape we will substitute the value of omega 1 out here, we will get the mode shape for the first frequency, and after that we will substitute the value of omega 2 and we will get the mode shape for the second frequency. Okay. So, this is the equation in terms of R. So, the equation in terms of R1 and R2 here we are getting. Okay. So, this is the amplitude ratio, which is nothing but A2 over A1. Okay. So, for first frequency and this corresponds to for the second frequency. Okay. So, in the first case we have substituted omega 1 and in second case we have substituted omega 2. Okay. So, we are putting the values of omega 1 square. Okay. So, here we get the value of first mode. Okay. So, here if we are assuming this thing as the card system that was given out here. So, it means that if the first mass moves towards right 1 unit, okay, the second mass again will move in the same direction 2 units. Okay. So, this is the ratio of 1 and 2. Okay. So, if we use our beam analogy, okay, and we say that the two masses are assumed to be concentrated at this 2 degrees of freedom. Okay. So, it means that if this one has moved vertically 1 unit, the other one is going to move vertically 2 units. Okay. So, it should look like this. Okay. It should obey the boundary condition. So, it should be looking something like this, okay, which is drawn out here. Okay. So, this is the first mode shape correspond to the first frequency. Okay. So, in this first frequency the system is going to vibrate like this. Okay. So, the motion will be synchronous motion in which both the things, both the masses will move either toward the right or toward the left or oscillate towards the mean position. Okay. The first mass oscillating 1 unit and the second mass oscillating 2 units. Okay. So, this is the interpretation of this term. Okay. Similarly, we write down the value of second frequency, okay, and we calculate the value of R2. Okay. So, the second mode comes out to be 1 and minus 5. It means that if we looked into the system again, if the first one is moving 1 unit towards the right, the other one is going to move 5 units towards the left. Okay. So, this is the interpretation of plus and minus out here. Okay. So, if we look into our beam analogy, okay, and if we assume 2 concentrated masses out here following a boundary condition, then if this mass is going to move 1 unit in the downward direction, this mass is going to move 5 units in the other direction. Okay. So, this is how the mode shape is going to look like, okay, which is shown out here. The first one has moved 1 unit towards one direction, the other one has simultaneously moved 5 units in the other opposite direction. Okay. So, this is the mode shape for the second mode. Okay. So, this is intuitive also because we remember that if you have a uniformly distributed beam, okay, if the distribution of the mass and stiffness is uniform across the section, okay, then the section is going to behave like this. Okay. The actual behavior, the continuous behavior will be a sinusoidal behavior, okay, and this is the discrete behavior because we are assuming that the masses are concentrated at these 2 points, and here in this particular case this value will be same, it will be 1 and 1 unit because the distribution of the mass and stiffness is uniform. Since in this particular question the value of the mass and stiffness are different, okay, first mass is 10 and second mass is 1, okay, and the value of the stiffness is also non-uniform, So, it will exhibit a behavior which mimics this shape, but the values of the mode will be different. Okay. So, if we take out the same examples, the similar example from the last time, in the last time what happened was, the value of the stiffness and the value of mass was uniform for the entire section. Okay. So, value of k, all k was same and the value of all m was same. Okay. So, in this particular case, when we evaluated the mode shapes, okay, it came out to be 1 1. Okay. It means that it was mimicking this behavior. Okay. So, this behavior boundary condition, it will be 0 0, and if there are two concentrated masses, if one mass moves 1 unit towards the bottom, other one is also going to move in the same fashion. Okay. So, this was the mode shape. Okay. But in this particular mode shape, okay, since the distribution of the mass is different, mass and stiffness is different, okay, the movement will be non-uniform movement, but it will mimic the general nature. Okay. So, similarly for the second frequency in the previous case, okay, if first mass was moving 1 unit towards in the downward direction, the other mass was also moving 1 unit, but in the opposite direction. So, this was the mode shape. Okay, for the uniform case. Okay, mass and stiffness distribution is uniform. Since in this particular case the mass and the stiffness distribution is non-uniform, then the magnitude of the mode shape is slightly different. Okay, but it follows the general trend of the second mode. Okay. So, we can again increase the complexity and put 3 masses out here. Okay. We could have put 3 masses also. Okay. So, this becomes a 3 degree of freedom system, and if we analyze the 3 degree of freedom system, then the distribution of the modes will be something like this. Okay. So, it will follow this general nature. The relative magnitude can be different depending upon the distribution of the masses and the stiffness. Okay. But it will follow the generalized nature like this. Okay. And similarly, we can extend the complexity of the problem and we can further keep on adding the different masses. Okay. So, we established the frequencies, we established the mode shapes. So, first frequency, the corresponding mode shape we have established, second frequency and the corresponding mode shape we have established. Okay. Moving ahead. Okay. So, the general solution for the 2 degree of freedom system. So, this is the general solution for a 2 degree of freedom system. Okay. So, if you look closely, what we are seeing is that each degree of freedom will be a summation of the individual frequencies. It will be a contribution from the individual modes. Okay. So, this is the shape function and this is the amplitude component due to the time dependent component. Okay. So, x1 will be summation of q1 phi 1 plus q2 phi 2. Okay. And similarly, x2 will be x1 1 coefficient, okay, x1 1 coefficient, x1 1 2 coefficient. Okay. And similarly, the same modal contribution from the second mode will occur. So, these are the amplitude components due to the time dependent part. Okay. So, these are the amplitude components, okay, values of qn and phi n. Okay. And this is due to the frequencies of the system. Okay. So, the total displacement for each degree of freedom will be a function of the individual modes multiplied by a amplitude component. Okay. So, after that we substitute the values. Okay. We substitute the values of R1 and R2 in the equation. Okay. So, we get this 2 equations. Okay. And again substituting, okay, we are rearranging and writing the terms out here. Okay. So, this way we are trying to solve the problem. Okay. So, R1 and R2 for the first frequency. Okay. So, this is basically, this was A1, A2. Okay. So, this was the component due to A1, A2. So, the first frequency R1 we have evaluated as 1 and 2. Okay. So, if this was 1, this will become 2. Okay. And for the second one we have evaluated this thing as 1 and minus 5. Okay. So, that is what we are trying to put out here. So, this was 1 and 2 and this was 1 and minus 5. So, this is what we are writing out here. Okay. 1, 2, 1 and minus 5. Okay. And here we are rearranging the equations. Okay. So, now what we need to do, we need to find the values of A1 and A2. Okay. So, we use the initial condition. Okay. So, this is an initial condition problem, meaning here the vibration is caused due to an initial condition, okay, or an initial vibration in the system. Okay. So, there is no forcing function is 0, okay, and there is a displacement of 1 unit at the first degree of freedom. Okay. So, what has happened out here is that, and the velocity components and displacement components other positions are 0. Okay. It simply means that this system is at rest, and at time t equals to 0, this has been pushed 1 unit in this direction and left. Okay. So, it has been pushed 1 unit and then it is left. Okay. So, due to this initial displacement, this system will try to oscillate. Okay. So, these are the initial conditions. Okay. So, these initial conditions will put into the two equations in order to calculate the values of the A1 and A2 components. Okay. So, first equation we put down the values. So, displacement at time t equals to 0 equals to 1. Okay. So, time t here, time t equals to 0, here time t equals to 0, and for the second case, for the second degree of freedom, initial displacement is 0, x2 equals to 0 at time t equals to 0. Okay. So, we get the two equations. Okay. So, we get the value of A1 and A2. Okay. After that, we do the same thing for the velocity part. Okay. And from the velocity part again we solve for the different components. Okay. So, here are two unknowns are there, A and phi, the amplitude component and the phase lag. Okay. So, amplitude component we have calculated out here, and we again put back these values out here, and we calculate the phase lag in the system. Okay. So, we get the value of the phase lag, okay, of the system. Okay. So, we have calculated all the four unknowns A and phi, okay, the value of the amplitude component and the value of the phase lag. Okay. So, now we have the complete picture of the vibration of the system. Okay. Okay. So, we back substitute the values of omega, which we have calculated first. After that, we calculated the value of A1, A2, phi1, phi2, okay, via the initial condition. Okay. And then we get the total solution for the 2 degrees of freedom. Okay. So, this is the final solution, okay, for this particular case. Okay. The amplitude component, okay, frequencies and the phase lag. Okay. So, this is the solution in the matrix form. Okay. So, here in this particular example, what we did was we were given a 2 degree of freedom system, and the corresponding values of mass and stiffness was given. So, in this particular case, what we did was we first formulated the we first drew out the free body diagram. After drawing the free body diagram, we wrote down the equation of the motion. After we wrote down the equation of the motion, we formulated the equations in a matrix formulation. From the matrix formulation, we put down the individual values of the mass and the stiffness from there. From that value, we calculated the frequency of the system. From the frequency of the system, we calculated the mode shape of the system. Okay. And mode shapes, we checked and established the mode shapes that it conforms to our pre-established notions. Okay. So, it agrees with our physical interpretation of the system. So, once we did that, after that we evaluated the initial condition of the system. Okay. The initial conditions of the system are given. So, we put that thing into the equation, and we evaluated the time dependent component A1 and A2, and we evaluated the phase lag in the system. Okay. So, from there we have calculated all the unknowns, the frequencies we have calculated, the amplitude we calculated, and the phase lag we calculated, and from there we were able to write down the equations for the motion of this system for the chosen degree of freedom in the matrix form. Okay. So, this is the complete step by step how we solved for the 2 degree of freedom system. Okay. Okay. So, the same thing can be expressed in this form also, okay, and we can write it as. So, here we can see we can write in terms of sine component also, and we can write in terms of cos component also. Okay. So, the thing that needs to be seen out here is that for each of them is a function of the individual frequencies. Okay. So, this mode shape is coming from the frequencies. Okay. So, this sinusoidal mode shape corresponds to the omega 1 and this sinusoidal mode shape corresponds to omega 2. Okay. And there is a amplitude component, okay, an amplitude factor. Okay. So, each solution will be, or each degree of freedom motion will be a solution of the summation of all the involved modes. Okay. So, all the modes will be there and they will be multiplied with a corresponding amplitude function. Okay. So, here corresponding amplitude function, okay, and the contribution from the particular frequencies. Okay. So, remember, for each chosen degree of freedom, the total solution will be the component from the all the degrees of freedom multiplied by the amplitude component corresponding to the initial conditions or the forcing function. Okay. So, moving ahead. So, now we will try to do one more example. Okay. Here also we have been given a 2 degree of freedom system, okay, where mass is given. Okay. So, all given 2 masses are same and the value of 2 stiffness is same. Okay. So, first what we need to do is that we look into the system, okay, and we try to see how many degrees of freedom are there in the system. Okay. So, we go back to our previous rule, okay, and see how many number of degrees of freedom are there in this particular system. Okay. So, our rule was that we have to look into the number of masses in the system and then we have to look into the individual motion for each mass of the system to calculate the total number of degrees of freedom of this particular system. Okay. So, we will again follow this particular rule. Okay. So, here in this particular case we have 2 masses, okay, we have mass m1 and we have mass 2 m2. Okay. So, this is mass 1, this is again a second mass. Okay. So, what it can do is that in this particular case this mass can move in the vertical direction and this mass can also move in the vertical direction. So, this the movement is 1 here and the movement is 1 here. So, 1 cross 1 1, 1 cross 1 1. So, it comes out to be a 2. Okay. So, there are 2 degrees of freedom in this particular system. Okay. So, we have established that this is a 2 degree of freedom system. Okay. Now, forcing function. So, there are no forcing function in this system. So, this is a case of free vibration, okay, simply meaning the external forcing function is 0 and there are no damping present in this system. Okay. So, the total damping present in the system is 0. So, this becomes a case of undamped system. Okay. So, this is an undamped system, okay, C equals to 0. Okay. So, we have established that this is a case of a 2 degree of freedom system. The motion is the vertical motion or the vertical translational motions at m1 and the vertical translation motion at m2, okay, at the 2 masses. The forcing function is 0 and this is a case of an undamped system. Okay. Now, how the system is going to behave? Okay. The system is going to vibrate due to the initial conditions. Okay. So, initial condition, okay, at time t equals to 0 there is a motion x1, at time t equals to 0 there is a motion x2, okay, and there is a velocity is also there. There is an initial velocity and there is an initial displacement in the system. Okay. So, these are the initial condition. Okay. So, initial condition can be any mix and match of the initial displacement and the initial velocities, okay, that will cause the system to vibrate. Okay. So, this is how the system is set up. Okay. So, we have already seen an example to solve this problem. Okay. We have described the system, we have set up the conditions of the system. So, I would request you to practice this question, okay, and in the next class we will continue with this solution and we will try to see how the system is going to vibrate. Thank you.